All right, what's up, everybody? Welcome back to Structure Free Learning. And in this video, we're going to do an example problem using the method of virtual work, or also called the unit load method, to determine the slope or rotation at a specific point on this beam here. This beam has an overhang for segment CA, and then it's roller supported at A, has a pin support at B. You got the loading, it's uniform over segment CA, and then linearly distributed over segment AB. If you're interested in drawing the shear and moment diagram, I have a link for you here to the video for a shear and moment diagram. Now, what we're going to do in this problem is use a unit load method, or the virtual method of virtual work, which is based on the idea that the work of all the external loads is equal to the internal work, or the work done by all the internal loads. And in most cases for beams, we're going to neglect the work of axial loads and the work of shear loads. And so we'll only be worried about the work associated with the internal bending moment within a beam. And so usually the relationships that we use for the method of virtual work are these. This first one is if you want to find the displacement at a specific point, and you would integrate or find the internal energy for the entire length of the beam and compare that to the external work done by a unit virtual force. And if you're trying to find a rotation, you would apply a unit virtual moment, which I have called mv here, to find this slope or rotation, and then you would again integrate over the internal work. And if you're interested in where these equations come from and a little bit more detail, then guess what? Another link for you here. Now in this problem, because we're interested in the slope, we're going to be using this formulation here with the unit moment. So we're going to apply a unit moment as part of our process to calculate this slope at point C. So now, instead of trying to remember or memorize a process for this, if you understand this relationship, really the process and the approach that you need to solve this problem are all embedded in this relationship. And so here, you know that we're solving for this unknown right here, this theta C, the slope at C. I need to have another structure, the same schematic, the same geometry, with a unit virtual load. And for that unit virtual load, or that same beam geometry that I have here, this overhang beam, with that unit virtual load, I want to determine the moment functions or moment diagram, and these will give me my virtual moment functions. And the last part that I also need is this portion right here, which is the real curvature. Because EI is constant, what I really need are the moment functions due to the externally applied loads, or the real loads. And in this case, the real loads are this uniformly distributed 8 kip per foot and this linearly distributed load on that span AB. And once I have all of those parts, I just got to integrate, and then I'll be able to solve for theta C, or the slope at C. You don't really have to follow any specific order. Like I could do the pink stuff first, or I could do the orange stuff first. So it's really up to you. So because I have the schematic for the real loads, if you will, drawn right now, I'll just go ahead and do that first, which means I need to get the moment functions so I can determine this real curvature function over the entire length of the beam. So now I'll just focus on the real structural analysis, which just means I'm trying to find the curvature function, this m over EI function for the entire length of the beam. And to do that, the first thing that I'm going to do is really just like what I learned in statics, is determine my support reactions. And so I'll draw a free body diagram. I'll just use a diagram that I have here. So I've got this AY, BY, X, and let's see, from some of the forces in the horizontal, I'll get that BX is 0. I'll take moments about point A, and here I would have a resultant of 48 kips. That is 3 feet from A. And then for the linearly distributed portion, I'll have a resultant of 1/2 the base times the height. So 1/2 of 8 times 9, which is 36 kips from A, 1/3 of 9 feet. So this is 3 feet. And if I take moments about A here, I would get 48 kips times 3 feet minus 36 kips times 3 feet plus by times 9 feet equals 0. And this would tell me that by is negative 4 kips. And what that negative means is that the direction of by is opposite of what I drew. So it's actually 4 kips pointing down. And now, last but not least, I could just sum forces in the vertical direction. And this will be, let's see, I'll have negative 48 kips plus ay minus 36 kips minus the 4 kips, which is pointing down, equals 0. And here ay would be 88 kips pointing upwards like this. Those are my support reactions, and once I have those, I'd like to redraw my beam structure with the support reactions all drawn in. So I'll go ahead and do that. Then I'll be able to start determining the moment functions. So here's my structure with the loading and the support reactions all drawn in. And now what I want to do is determine my moment functions. And if you need a recap on moment functions, hey, I think I got one in the I got a link to the upper right hand corner there. All right. You know, the thing that I like to do with the moment functions is I got to figure out how many functions do I need to describe basically the moment diagram for this entire beam structure. And what's important is to identify the discontinuities. So discontinuities, if you've seen any of my other videos, you realize that discontinuities are beginnings and ends of distributed loads or concentrated forces or moments. All of those are going to present discontinuities in our shear and moment diagrams. And so here in this case, I have 1 at C because it's the beginning of a distributed load. It's also a free end. At A, I have a discontinuity. It's the end of the uniformly distributed load. It is also the beginning of the linearly distributed load. It is also where I have an 88 kip concentrated force. And then point B here is also another discontinuity. It is the end of a distributed load and the location of my 4 kip concentrated force or support reaction there. I have 3 discontinuities, and so for my moment functions, that means I need to make 2 cuts. And so I'll have a cut 1 and a cut 2. And for each cut, you want to choose or establish a local coordinate system. For cut 1, before I choose an origin, the origin should always be at a discontinuity location. So in this case, I would choose my origin if I want to go left to right at point C here, and I would go like this. And I'll call this x1, like that. And then for cut 2, again, I can choose any discontinuity for my cut 2. I could choose C, I could choose A. I'll just happen to choose B here, and I'll call this x2, my other coordinate system for cut 2. And the range, based on my choices, so for instance, x1 is from discontinuity to discontinuity. At point C, x1 is 0, so it starts at 0 and goes to A, where at A, it would be 6 feet. So that is the range for x1. And then for cut 2 here, the range of x2 would be, well, it starts at B, and B is the origin, so it'd be 0 at B, and goes all the way to A, from discontinuity to discontinuity, and that would be 9 feet. And those are the ranges for the coordinate system. Now, to determine the moment function, all I have to do is cut, draw a free body diagram, and apply equilibrium equations. And so here for cut 1, I will draw a free body diagram. I can choose either the left or the right side of the free body diagram. I will choose the left side here. So if I choose the left side of that cut, here is what my free body diagram will look like. And here's the face of that cut. The distributed load here is 8 kip per foot. And here, this is x1. And here I could have a normal N1, a shear V1, and a moment M1. Now I could determine all 3 functions using the equilibrium equations, but what I really just need is the moment function. So to get the moment function, I could just sum the moments about the cut. like this. And this would tell me that M1, so here this M1, the concentrated M1 here, and let's see, this distributed load here will have a resultant of 8 kip per foot times X1, and the arm, in this case here, is X1 over 2. And so the moment contribution of this distributed load would be, it's also going to be positive, or it's going to be added. It's going to be the resultant, which is 8 kip per foot times x1, that's the resultant, times the arm, which is x1 over 2, and all of this equals 0. And this would tell me, when I solve for m1, it will tell me that my moment function m1 is negative 4 kip per foot times x1 squared. And that is my first moment function. And if I want to turn that into a curvature function, in this case, because this flexural rigidity EI is constant, I can just divide by EI, and this would become the curvature function M1 over EI. This would be my curvature function that I'm going to use later. Next, I would look at cut 2, and for my cut 2, I'm going to make that cut, and I'm going to choose the right side of that cut to draw the free body diagram. So that would look something like this. And I don't know what the intensity of that value is there, but I can solve for it by either using a linear function in terms of x, or using similar triangles, which I'll show you in a second here. But this is cut x2 like this. And again, on the inside, I would have a moment, a normal, and a shear. But I don't need the normal function. I don't need the shear function. I just need the moment function. So if I take moments about the cut like this, then I would get, let's see, I have the concentrated M2, so negative M2. Linearly distributed load will have a resultant, use W star for now, but this distributed load will have a resultant that is 1/2 W star, I don't know what that is, times x2, like this, and the resultant here, this distance, would be x2 over 3 for the location of the centroid of a triangle. And so the moment contribution for this, for the distributed load, would be, let's see, it's also negative, so it would be negative, the force resultant, 1/2 W star times x2 times the arm of x2 over 3. And then I have this 4 kip, don't forget that concentrated force there, minus 4 kips times x2, and all of this equals 0. And after some algebra, yes. So the question now, we're not done yet, is what is W star? Well, if I go back and I look over here, if I go back to this drawing right here, here is this W star location. And by similar triangles, I could relate this height to this height here. Can you see that? Here, let me use a different color. From here to here to here to here. Yes, right? So I have, if you will, this triangle versus the larger triangle here, like this. Yes, maybe a little bit difficult to see. But what that tells me is, I know that the height here is 8 kip per foot over a length of 9 feet. So by ratios, I would know that here, this would tell me W star over x2 is equal to 8 kip per foot over 9 feet. And this would just tell me that W star is 8/9 kip per foot squared times x2. And I can take this and bring it and substitute this into my W star down here. And this would give me that M2 times x2 squared. And with a little bit more algebra, this would be my other moment function, like that. And again, because EI is constant, I could just turn this into my curvature function just by dividing by EI. Yes, 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 yes. All right. So really that feels like half the problem because half the problem is determining these moment functions. Oh, maybe it's a third of the problem. And so this is really something you learned back in statics that hopefully you are still able to do. You know what I'm saying? So far, now if I go back and I look at my equation that's kind of guiding everything that I'm doing, what I've accomplished so far, and I love check marks, so what I've accomplished so far is the moment or real curvature portion. Check. Yes. Okay. And so now I want to do my virtual structural analysis, which will involve me drawing this overhang beam again and then applying the unit virtual load. And this, it'll be a unit virtual moment because I'm trying to get a rotation or a slope in this case. And then I'm going to determine the internal moment functions again. And so if I go down, ooh, it's like a new page. And so here, I'll call this part two. This will be my virtual structural analysis. So this time, I'm only bringing the geometry with me. So this overhang beam, I'm going to apply that virtual moment with a magnitude of 1, a unit virtual moment at C right here. And I'm going to guess a direction. So I'm going to guess, what is this, counterclockwise. And this will have a virtual moment mv equal to 1 kip feet. And here is my virtual structure. This M, capital MV, is my virtual load, my unit virtual moment. And now what I want to find in this problem is really the moment functions. We call them virtual moment functions because of the virtual load that's applied, okay? And I'll give it a lowercase m. Now the key here, what you really need are to have the same coordinate systems that you used in the real structural analysis in order for you to make sure that when you integrate, we want to have the same bounds for each of the functions. Up here, we want to multiply the functions together and make sure that we start and end in the same way. We're speaking the same language, if you will. Here, I chose x1 with an origin at point C. I chose x2 with an origin at B, and these were the same. These were the ranges for x1 and x2. I want to have the exact same situation in my virtual structure or my virtual drawing. This is probably where a lot of mistakes typically occur. Is because people just try to be as convenient as possible when they draw the moment functions instead of thinking about what was done before. And so we want to follow the same cut. So we'll call this cut 1, and we're fortunate, at least in this case, that we have the same discontinuities. C, A, and B are also discontinuities because we would expect support reactions. Oh, time out! And even before we do all this, I kind of jumped ahead, but here, before I get all crazy right here, this would be cut 2 like this right there. Okay. Right there. But I jumped ahead, I jumped ahead a little bit. I need the support reactions for this virtual structure before I can proceed. And that just involves a quick free body diagram, AY, BY, BX. We already know BX is 0 if I sum forces in the horizontal, so no big deal. Take moments about A equal to 0 in this case, and I have the 1 kip foot plus by times 9 feet equals 0, and it just tells me that by is negative 1/9 kip, which is equal to 1/9 kip going down like that. And then if I sum forces in the vertical direction, I will get that AY minus 1/9 kip equals 0. So AY is 1/9 kip pointing upwards like this. All right. And so in fact, I could probably replace these with the correct magnitude and directions. Yes, and now I can go ahead and determine moment functions. And so for cut 1, just as before, here is x1. And you'll always find that the virtual loading is a little bit easier to analyze because it's not as complicated, right? It's just a single concentrated force or moment, in this case moment. And so here, cut 1, I'll choose the left side of that cut again. No big deal. Boom. Right here, I have the 1 kip foot. On the inside of the cut, I've got a moment. I'll call it a lowercase mv1, right, for the virtual moment. And there would be a normal and a shear as well. But guess I don't need it. You know what I'm saying? I don't need it. I don't need it. I'll call this x1. And just like before, if I sum moments about the cut equal to 0, I will get mv1 plus 1 kip foot equals 0, and that just tells me that the moment diagram is constant over this segment CA for the virtual structure, and it's negative 1 kip feet. This is that internal moment function that I need to solve this problem. Yes, yes, yes. And then for cut 2, boom, again, I'll say the origin at B just like before. Here is x2 like this, and for that cut, again, if I choose the right side of the cut, my diagram, my free body diagram will look like this. I'll have the 1/9 kip pointing down, the x2 like that, and then I'll have here mv2. And then there'd be a normal and a shear as well, but we don't need those. We don't need those. We're not including those effects at all. And so here I would have, from some of the moments about the cut, I would get that, let's see, negative mv2 minus 1/9 kip times x2 equals 0. And here, this mv2, it's linear over this segment. All right, not bad, not bad. So those are all my moment functions. So let's go back up to that checklist or the equation. And yes, and so here, let me give myself some checks because I love the checks. Did I draw a structure with a unit virtual load applied? Yes, I did. Check. Did I determine the virtual moment functions that I need for the virtual loading structure? Yes, I did. Check. So what I got to do now is just apply the principle of virtual work and solve. And so here's that principle of virtual work. Now that I have it, this 0 to L here means that I have to integrate over the entire length of the beam, not just one span or one segment of the beam, but the entire length of the beam. So deal is we have to separate this out into parts because we have 2 coordinate systems or 2 cuts essentially that we made. So we're going to break this integral up into 2 parts. So I know the virtual moment is a 1 kip foot that I applied. Theta c is the unknown that I'm trying to solve for. And now I got to plug and chug the moment equations, right? And so my first segment, I'll call that function 1. This x1 coordinate system was from 0 to 6 feet. And here, this will involve mv1 times m1 over ei integrated with respect to x1 like this. The second system, or the second cut, if you will, is here. And that was going from right to left from 0 to 9 feet. And that will be mv2 times m2 over ei with respect to dx2. And now we just got to plug and chug and integrate, you know what I'm saying? So here, this, again, I'll keep the left side, is equal to, and now I just got to integrate, which is really not that bad. It's just a polynomial, you know what I'm saying? All right, and if I look at the units here, if I divide kip and feet, I can get rid of 1, and this will leave me with kip feet squared. And so my final answer is that theta c, the slope, is 590.4 over ei kip foot squared. The slope should be dimensionless or in units of radians, but this EI also has units of kip feet squared, so they'll eventually cancel out if you have to plug in numbers for the modulus of elasticity and the moment of inertia. So this is my slope. It has a magnitude of 590.4 over EI kip feet squared. The direction, because the answer that I got is a positive result, the direction is in the same direction as I drew the virtual moment. And if I go way back to my virtual structure, you'll see that I drew my virtual moment in the counterclockwise direction. So the rotation at point C should be like this. All right, so the question is, can you do the exact same problem now for the vertical displacement at point C? What would change for you if you had to do or determine the vertical displacement at point C? All right, hopefully this was a useful video. Take it easy. Structure free.